Today we're going to be talking about parts of similar triangles. So first of all, let's look at two triangles here, and they each are going to have an altitude. And remember that our altitude is always going to make a right angle with the opposite side. It starts at a vertex, makes a right angle with the opposite side. Okay, so we're looking at these two triangles here. We'll call them triangle ABC and triangle DEF. And on these two triangles, we're already told that the two triangles are similar. So they will have some kind of similarity statement, or they will have written in words at the beginning, triangle ABC is similar to triangle DEF. Okay, and that's a really important first piece of information. And so then we're interested in knowing what would be the comparison or the relationship between those altitudes. And so our rule, which we're starting on 7.5, right, so that's on page 501 in your book, our rule says if you have two triangles that are similar, then the lengths of the altitudes are proportional to the lengths of the corresponding sides. Okay, so let's go ahead and I'm going to give this a name down here. So we'll call this G and we'll call this one H. So we can name our altitudes. And so we're going to say BG, the altitude of the first triangle, over EH, the altitude of the second triangle, would be equal to BC over EF. And I've gone ahead and color-coded each of those lines so that you can see where I'm getting those from. And some of you are probably wondering, why did I pick BC and EF? And the truth is, those are just two corresponding sides. So I could just as easily have chosen, instead of BC, I could have chosen, BA, and then instead of EF, I could have chosen ED. And that's fine, as long as it's two corresponding sides on the same, or on the two triangles. Okay. All right, so our next rule is going to be talking about angle bisectors. So again, we're going to have two triangles, ABC and DEF. And on these two triangles, we are going to draw an angle bisector. So we're saying that this angle and this angle are congruent, and we are saying that this angle and this angle are congruent. Okay? And we'll go ahead and call this, let's see, A, B, C, D, E, F, G, and H again. And so this time we're dealing with angle bisectors. So if we have two similar triangles, so again, they have to tell you triangle ABC is similar to triangle DEF somewhere, and that could either be in a similarity statement like this, or it can be in words. But if they tell you that, then you will know that our angle bisectors are going to be proportional to the corresponding sides. So that means that we could say BG over EH is equal to BC over EF. Okay? And again, instead of EF, you could have chosen ED, and instead of BC, you could have chosen BA. That would be fine, as long as you have corresponding parts. So if you did use BA, it would have to be BA over ED, because those are the corresponding sides. All right? So that's if we have angle bisectors, then those are going to be proportional. Okay, so on here, our next rule is going to be about medians. So we, again, are going to start off with two similar triangles, ABC and DEF. And the medians are going to be drawn from one vertex to the midpoint of the opposite side. Okay, so remember that means that these two portions over here would be congruent. And same thing on this one. Oops, that looks like a different letter than I meant for it to. All right, so we've drawn our two medians, and this time we're going to know that if the two triangles are similar, then their medians, BG and EH, are going to be proportional to the sides. So again, that would be BC and EF. And again, you could have also had BG over EH is equal to BA over ED. Right? That would be the same thing. So it doesn't matter which of the sides, it just has to be one of those sides. And they have to be paired up with a corresponding side on the other triangle. Okay? So that's going to be really helpful because they're going to give us measurements for these different line segments, lengths. And so then we can solve for other lengths when we need them. Okay, so we have one more rule. Okay? And this one is going to be talking about the angle bisectors again. So you'll notice we talked about the angle bisectors here. And we were talking about the angle bisector length itself is proportional to the corresponding sides. This time, instead of talking about the length of the angle bisector, we're actually talking about the line segments it cuts over here on the side. So, for example, this is our angle bisector, JM, right? And it cuts this line, KL, into two pieces. So we have KM here is one piece, and ML is another piece. And so we are able to say KM is proportional to ML, and that would be equal to the two sides. Now, when we're matching these up, you'll notice KM is up here at the top, and the side of the triangle that touches that piece is over here. It is KJ, so it has to go on top where KM was. And ML over here, this half, or this piece of that line segment, touches JL down here, so, or LJ, doesn't matter which order. Okay, but so it has to be on the bottom where ML is. Okay, now obviously these could be flipped and that would be fine, but it's important that if you put KM on top, that KJ is on top of the other half of that proportion, and if you put ML on bottom, that LJ is on the bottom of the other half of that proportion. Okay, so we'll go through a couple of examples to look at these tomorrow. Keep in mind, especially on this one, that we are not saying that KM and ML are congruent. They could be, or they could be something completely different. We're just saying that they are proportional. Okay, so that's going to be important. So I will see you tomorrow in class. Thank you. And don't forget that we have 0 hour Monday through Thursdays in the morning. You can come in anytime. Thank you.